This video is going to be about capacitors, okay? So the title is capacitors. We closed the video about electric fields by discussing about uniform fields, which is gonna be our starting point to talk about capacitors. So we already talked. And those of you who didn't watch the video, please go and watch the last few minutes of the electric fields video. So we already talked about the electric field between two parallel plates. And the equipotential lines in this field. So a parallel plate capacitor is just two parallel plates that create a uniform field that look like this. I'm not gonna use different color this time. So this is the positive plate and this is the negative plate. Okay, the electric field is always perpendicular on the charged surfaces, as we saw. So this is what the electric field looks like. And we need arrows because recall that the electric field is a vector quantity. The more charge there is on a capacitor, the denser these lines will be. Okay, let me erase this little part here. And the equipotential lines are perpendicular to electric field lines. Okay, and anywhere on these lines, anywhere on this line or anywhere on this line, etc., the potential is the same. Okay, and by the way, the plates itself, so the positive plate and the negative plate, are also equipotential lines. Okay, now if the potential difference between these two plates is V, so you can think of, say, a battery maybe applied across these two parallel plates, creating a potential difference of V. And if the distance between these two plates is D, then the electric field is simply V over D, and the direction is downward. So if you write it as a vector, it should actually be minus V over D, because the direction is in the negative side of the y-axis, but you don't need to consider this. Okay, now let's put this thing, the capacitor, into a circuit that includes a battery and see what is going to happen. So let's put the capacitor into a circuit with a battery. So the situation is going to look like this. By the way, this is how a parallel plate capacitor is drawn in electric circuits. This is my battery, plus side, the minus side, etc. So actually, let me, where is the lasso here? Let me make some space for me, okay. All right, so what's gonna happen immediately after we put the battery? So this denotes like a time evolution, I guess. So I'm gonna draw the circuit again, plus, minus, and this is the parallel plate capacitor. So the positive plate is gonna start drawing electrons from the one plate of the capacitor, okay, and push them onto the other side, okay. So an electric current will start appearing in the circuit due to this flow of electrons, okay? But this flow is not going to last forever, because eventually all of the electrons that can be moved from the one plate of the capacitor will move to the other plate. And by the way, we start with a potential difference of 0. So right before we, sorry, it should be VC. Okay, it should be so VC is 0 initially, so immediately before putting the battery in, the potential difference across these plates is 0. But once the potential difference across the plates of the capacitor becomes V, the same as the battery, and by the way, the potential difference of the battery is V, then all electrons will move to the right-hand side of the capacitor, and because there will be no electrons on the left-hand side of the capacitor, it will be positively charged, okay? So this is the final state. This is the final state of the capacitor. So this is now a charged capacitor, as we say. So what is a capacitor really? A capacitor is a device that stores charge. Before we move on, there is one more thing I want to talk about regarding the circuit we just studied, this one. So recall that current is the change in current with respect to time, dq over dt, or delta q over delta t. So if delta t is really small, about equal to 0, which is the situation immediately after we install the battery in this circuit, okay, the current, if delta t is really small, the current will become infinite, right? Because dividing by a really small number gives us a really large result. So will become infinite. So I is going to tend to infinity. So realistically, we need a resistor in the circuit. So that the flow of charge is reduced. So a realistic circuit that includes a capacitor looks like this. So you have your capacitor, you have your resistor, and you have your battery. And this is fine. This is not a circuit that is going to go toasted because the current becomes infinite. So now let us assume that we have a charged capacitor. Assume we charge the capacitor, and remove the battery from the circuit. Replacing it with a light bulb. So the situation is going to look like this. This is our capacitor, and as promised, we said that it is charged, okay? So instead of the battery, we now have a light bulb, okay? And this is the symbol for a light bulb. We have a resistor. As we discussed, we need a resistor in our circuit. Now, what's going to happen once I remove the battery and install the light bulb? So recall that this is at a higher potential, right? Higher potential compared to the negative plate. Therefore, electrons are going to start flowing in this circuit, right? Therefore, the potential V of this capacitor is going to start dropping gradually, okay? Eventually, it's going to become 0. But as the electrons flow, the light bulb will start glowing, right? Until all electrons are moved from the negative side of the negative plate of the capacitor to the positive, and then the flow of charge will stop, therefore the current will stop, and the potential across the capacitor, which is initially V, is gonna drop to 0. Okay, so let's write this down. The charge will flow towards the higher potential, light up the bulb, and once all charge is gone, the light will go out. Okay, so far we have been talking about conceptual things related to the capacitor. Now let's go quantify things. Let's go define some quantities needed to describe capacitors, starting with the capacity itself. So the amount of charge stored in a capacitor per applied voltage is called, oops, I don't need a triple L, I need a double L, is called C, the capacitance of the capacitor. So C is Q over V, okay? And the units for the capacitor is the farad, for the capacity is the farad, which is equal to 1 coulomb over 1 volt, okay? So 1 farad is 1 coulomb per volt, okay? All right, there is nothing else I will discuss about the capacity. Now let's go plot Q versus V, or V versus Q. So plotting V versus Q. So since C is Q over V, then V is 1 over C times Q, which is of the form, let's write it here, Y is mx plus C, but C here is 0. M is the inverse capacity, Y is our voltage, and X is our Q. So if we plot this, we're going to get a straight line, okay? So V versus Q, straight line passes through 0, and we get a straight line, and the gradient of this line is 1 over C. Now the area under this curve is the area of a right triangle, right? So it's easy to find this thing. So if we call this, let's say that this is, I don't know, some value Q prime, and this is some value V prime, then the area is the area of a triangle, which is 1/2 Q prime times V prime. But remember when we talked about electricity, Q times voltage gives us energy. So what kind of energy is this? What does this express? It's the energy stored in the capacitor. So this is the energy stored in the capacitor. So the energy for a capacitor is 1/2 Q times V. And then this is also equal to 1 if we replace Q by C times V. This is also equal to 1/2 CV squared. And if we replace V by Q over C, we get that this is also equal to Q squared over 2C. So note, let's write some notes about this. So if we plot Q versus V, we also get a straight line. So Q and V, okay, the area under the curve is also 1/2 QV, but the gradient of this line is now C. Okay, so be careful with problems where they might actually have the reverse curve. Okay, another note is that it's what I began telling you and I stopped. So in general, the electrical potential energy is Q times V. But for a capacitor, energy, electric potential energy, is 1/2 QV. What happened to the other half? Well, it gets lost in charging the capacitor. So 1/2 QV is lost in charging the capacitor. So this is the plate. And for a moment, I'm going to pretend that there is no resistor, okay? So once we plug in actually, let me erase the electrons. So let me remove the charge. So this is the positive plate. So immediately after we install the battery, electrons start traveling from the one plate of the capacitor to the other. So let's say that the first electron was installed on the plate. Now the second electron, okay, will need to push against the repulsion from this electron in order to be able to be deposited on the plate. So this is why we say that 1/2 QV is lost in charging the capacitor, because as the electrons eventually gather on the one plate of the capacitor, they have to push against the repulsion from the other electrons in order to sit there on the plate of the capacitor. Okay, now let's go talk math now. So this next part is going to be more math intensive. I'm sorry, guys, but it's really important and it comes up in problems a lot. So charging and discharging equations. So let's do the charging first, okay? So let's assume that we have a capacitor. Let me make some room here. So this is my battery, V. This is my resistor, R. And let's assume I put a voltmeter. Let's make it blue. Okay, to measure the VC, the potential difference across the capacitor, okay? And what we expect to find is a curve that looks like this. So if we plot the voltage across the capacitor, with respect to time, we expect that the final value will be V. Initially, it will have a potential difference equal to 0, and gradually it's going to increase and look like that. So how are we going to make sense of this plot? So by the way, this should be a straight line. I'm sorry. So let's use Kirchhoff's laws. And you learn those at the AS level. So let me make sure I'm not misspelling Mr. Kirchhoff's name. So Kirchhoff's law, okay, of potential differences pretty much. So as we walk around the circuit, so if we start here, we have to find that the sum of all potential drops is equal to whatever the potential difference across the elements is. So we have V, which is the potential drop of the battery, minus I times R, which is the potential difference across the resistor, minus Q over C, which is, so this is VR, this is VC, and this whole thing should be 0 because we walk around the circuit. Okay, so V minus IR minus VC should be equal to 0. Okay, now recall that current is dq over dt. So V minus, V minus R dq over dt minus Q over C. By the way, this should be C, not V, I'm sorry, is equal to 0. Okay, now that's a differential equation, a first order differential equation, which is kind of easily solved for those of you who are mathematically inclined. You don't need to know how to prove this, I think, but it's good to know. It helps with understanding. So let's rearrange this equation and write, I'm gonna bring everything to the right hand side. So actually I'm gonna multiply with -1 and get R dq over dt plus Q over C should be equal to V. And let me write 1 over C times V times Q, I'm sorry. Okay, now let me multiply with C. So R times C dq over dt plus Q is equal to CV. Okay, so that's equation 1. What kind of solution do we expect for equation 1? So one way to solve a differential equation is to go through techniques and solve them. But this is not a math class. I'm not going to attempt that. Instead, I'm going to try a trial function. So try Q being equal to Q naught times 1 minus e to the minus t over r c. Okay, so this is equation 2, where Q naught is C times V. This is the charge in the capacitor, on the capacitor, charge on C when C is fully charged. Okay, so let's take equation 2 and find its first derivative with respect to time. So from 2 we get dq over dt equal to Q naught over RC e to the minus t over RC. Okay, so let's name this equation 3. Now plugging 2 and 3 into equation 1 gives us, so from 1, 2, 3, we get that Q naught e to the minus t over RC plus Q naught minus Q naught e to the minus t over RC must be equal to C times V. This and that cancel, and we find that Q naught minus CV must be 0. But we said that Q naught is C times V, so C times V minus C times V is 0. So this equation works, okay? So thus Q equal to Q naught times 1 minus e to the minus t over RC, which is also equal to CV times 1 minus e to the minus t over RC, is the equation describing how charge changes in the circuit as we charge it, okay? So this V over here is the voltage of the battery, by the way, of the battery. Now, let's go talk a little bit about that constant RC. So RC has units of time. And it is called time constant, tau, and this is a Greek tau, okay, it's the Greek letter. Therefore, if we use that, so Q can be written as Q naught times 1 minus e to the minus t over tau. Okay, so this is an alternative form of writing this equation. And by the way, some of you are going to be curious about how on earth does RC have units of time. So let's try and prove that. So R is V, it's voltage over current. So it has units of volts per ampere, okay? C is Q over V, so it has units of coulombs per volt. Okay, so if we multiply R, C, in terms of units, okay, we're gonna have volts per, recall that 1 ampere is 1 coulomb per second, right? And then we multiply by C over V, so this cancels, so we get units of seconds, okay? So I'm not messing around, it's actually working, okay? Now let's go back to this equation and see what happens when t, this t, the English t, the Latin t, I'm sorry, is equal to the Greek tau. So if t is equal to tau, then q is q naught times 1 minus e to the minus 1, right? Which is equal to q naught times 1 minus 1 over e. Then 1 over e is 0.37, so, and recall that e is 2.71, right? So we get 1 minus 0.37, so we get 0.63 q naught, okay? Thus, after some time t equal to tau, 63% of the capacitor is charged. Okay, be careful because this is the charging curve. The same does not apply to the discharging curve. Okay, so let's see what's happening with the current in the circuit. So I is dq over dt, right? But we have the equation for q, and if we plug everything in, guys, please work this out on your own. It helps. Algebra helps. So q naught over RC e to the minus t over RC is what we get. But recall that q naught is CV. So C and C cancel, so we get V over R e to the minus t over RC. Okay, and we can call this I naught e to the minus t over RC. The RC, the time constant, is the same, and I naught is V over R. So if t is equal to tau, I is I naught over E, so 37% of current is left. Okay, and the final quantity is voltage. Voltage is simply the voltage across the capacitor. Voltage is simply Q over C, so it's Q naught over C times 1 minus e to the minus t over RC. So Q naught is CV, so C over C cancels, so we get VC is V times 1 minus e to the minus t over RC. So this is this curve is similar to the Q versus T curve. Okay, let's go plot these curves. Okay, plots. Let's make these plots for the charging phase. So let's start with the Q versus T. So we said that this is Q naught, which is equal to CV, right? Is it? Sorry, I got confused now. Yes. So this is the final value of the charge in the capacitor as we charge it. This is 0, and this is the form of the curve. Now, what's the gradient of this curve? So the gradient, grad, actually, let me bring this over here. So the grad is equal to delta Q over delta T, which is I, right? At time T. So if you find the slope at this point, this is the current at this time, let's call it T prime. If we go up here and we find the slope, we're gonna find the current at this time T prime. And notice something, the slope is maximum near the origin, near 0. And then the grad reduces, and eventually the grad becomes 0, right? This is exactly what we expect because of this curve. So the current drops to 0. This is what this curve tells you, which is what we see qualitatively in this graph, okay? So physics makes sense, sometimes at least. So let's go talk about the current versus time curve. So the maximum current is I naught, which is equal to V over R, and that's the maximum current at time 0. And we get a discharging curve, which asymptotically tends to 0 as time increases, okay? At time equal to tau, we get 0.37 I naught. And by the way, at time equal to tau on this curve, so let's call this tau, we get 0.63 Q naught, okay? Now, what's important in this curve is the area under the curve, which we might find in some problems. What is the area? Area is roughly equal to I times time. Okay, it's not I times time. You have to count the squares, these little squares, okay? If you're given the units, if this is, say, in seconds, so if 1 square represents 1 second, and if this is in amperes and 1 square represents 1 ampere, then this little square will represent 1 ampere times second, which is 1 coulomb, okay? So if we count squares under the curve, we will find the charge, okay? The total charge in the capacitor. So we will find Q naught if we count all the squares pretty much. All right, now let's go talk about the voltage versus time graph. So this is VC and this is V. This will have the same exact form, shape as the Q versus time graph, okay? If this is tau, this is going to be 0.63 volts. As far as I know, the area under this curve or the gradient of this curve have no physical significance. So I'm not going to talk about that. Let's move on. And move on to where? Move on to the discharging curves. So discharging curves. So this the situation here is simpler. We have a capacitor which we assume charged, a resistor, and we close the circuit, okay? If we apply Kirchhoff's law again, as we move across the circuit, now we only have voltage drops, okay? So it's a simpler situation. So VC plus VR is equal to 0. What is the potential across the capacitor? Q over C. What's the potential across a resistor? It's IR. So R, what is current? dQ over dt. What is the other one is not doesn't, yeah, we don't need to work on that. So R dq over dt plus 1 over cq is 0, okay? Let me get rid of the 1 over c. So RC times dq over dt plus q is equal to 0, where I multiply the left-hand side by c, okay? So again, we're gonna do a trial function. Try q is q naught e to the minus t over rc, okay? We're gonna plug this equation. So let's call this, we'll call the other equations 1, 2, 3. So this equation 4, this equation 5, okay? So we take 5 and we find the first derivative with respect to time, which is equal to minus q naught over rc times e to the minus t over rc. This is equation 6. So from 4, 5, 6, we get rc times minus q naught over rc, over rc times e to the minus t over rc plus q naught e to the minus t over rc is equal to 0. Okay, these rc cancels, therefore this and that cancel. So this works, okay? So this works. So q is equal to q naught e to the minus t over rc, and q naught, like before, is c times v, okay, where v is the voltage of the battery. So v of battery used to charge the capacitor. Okay, now if time is equal to tau, which is equal to rc, this time q becomes equal to q naught over e, so 0.37 q naught. So this time charge decreases exponentially in this circuit, okay? And at time equal to 1 time constant, the charge is dropped to 37% of the initial value, okay? Now let's go find the curves for current. So current is dq over dt. So if we find the derivative, we find that this is equal to v over r e to the minus t over rc, where this is I naught like before. So the current again drops in the circuit as we discharge the capacitor, just like the case when we charge the capacitor. And let's go talk about the voltage, which is q over c, e to the minus t over rc. So we simply get this q naught. So we get v e to the minus t over rc. So this time the voltage drops to 0 exponentially. So all the curves have the same form. So for discharging the capacitor, we get the same plots. They all represent exponential decay. So this is q versus t. We start from q naught and we drop exponentially to 0. At time equal to tau, which is the time constant, we get 0.37 q naught. Now the gradient of this curve is again equal to current at that particular time. So t prime in this example, okay? So because the gradient is equal to dq over dt, of course, okay? So the gradient of this curve gives you the current at a particular time. Now if we plot I versus t, then we also get an exponential decay curve, okay? And the area is equal to the total charge, okay? And finally, the voltage, Vc, voltage across the capacitor with respect to time, also drops to 0, starting from V, where V is the voltage of the battery used to charge the capacitor. Okay, and with this we are almost done, but there is one more thing I want to talk about. Let's talk about log plots. What are these now? Okay, so Q, recall that Q is Q naught e to the minus t over tau. So if we take the log on both sides, we get the ln of q is a ln of q naught plus ln of e to the minus t over tau. So ln of q is ln of q naught minus 1 over tau t. So this has the form of y equals to c, the constant, plus mx. So 1 over tau is the gradient. So if we plot this ln of q versus t, we get a straight line, which is easier to deal with. This graph starts at the ln of q naught, and the gradient is simply minus 1 over tau, which is minus 1 over rc. Okay? And I'm not gonna plot the log curves for current and voltage because they will be the same. So same curves for I and V. Instead, except that wherever we have a ln of q node, we're going to have a ln of I node, etc. Okay, and some miscellaneous thoughts. So miscellaneous, if we have, this is not part of your syllabus, but I'm going to mention it anyway. So if we have series capacitors, so if we have capacitors in series, 1 over C total is 1 over C1 plus 1 over C2. Okay, this happens because when we put capacitors in a series, nothing really changes in the circuit, okay, because they are still connected to the same battery. I mean, we still see the same amount of surface area pretty much because the charge is deposited on these plates, right? So we're not gonna get a lot of increase in how much parallel plates we have available to store charge on. And what I'm talking about is that if we put capacitors in parallel though, notice that now, if we put some voltage here, for example, and yeah, please imagine that that's voltage, okay? Then if this is C1 and C2, now C total is C1 plus C2 because now we have this plate to deposit charge on and this plate to deposit charge on. So we kind of have more surface area to deposit charge on. Whereas when we put capacitors like this, we have this surface area. And maybe this surface area is going to be slightly larger, but yeah, it's not going to have a large effect. But if you put capacitors in parallel, you get a pump, okay? You get a boost in the amount of charge you can store. And this is it for this video.